Hi there, future scientists. I am Atom, and I have got an exciting adventure in store for you. We are about to dive into the fascinating world of physics and uncover the secrets of momentum, impulse, and the relationship between the two. Now, let's kick things off with a fun scenario. Imagine we have a massive 1500 kilogram minivan and a medium-sized 10 kilogram bicycle, and they're both cruising at the same velocity of 5 meters per second. The question is, which one would be harder to stop, the minivan or the bicycle? Your gut feeling might be leaning toward the minivan, right? Well, let us put on our scientist hats and figure out why that's the case. These two vehicles are basically objects in motion. But here's the twist. The minivan has way more moving stuff, or what scientists call inertia, compared to the bicycle. According to Sir Isaac Newton and his first law of motion, also known as the law of inertia, it is harder to change the motion of something which has a lot of mass, like the minivan. The fancy term for this moving stuff, or inertia in motion, or mass in motion, is called momentum. And here is the secret formula for momentum. P equals mv, where P represents momentum, m represents mass, and v represents velocity. Now, let us do some math magic and calculate the momentum for both our minivan and bicycle. Minivan's momentum equals its mass 1500 kilograms multiplied by velocity 5 meters per second, which equals 7,500 kilograms meters per second. Bicycle's momentum equals its mass 10 kilogram times velocity 5 meters per second, which equals 50 kilograms meters per second. Wow! As you can see, the minivan has a whopping amount of momentum compared to the bicycle because the minivan has more mass. Here is another cool thing to notice. Momentum unit equals mass unit multiplied by velocity unit. Straightforward, isn't it? Now, here are a couple of challenge questions for you. How can an object with a small mass possess significant momentum? Pause here and check your answer. Since P equals mv, even if the mass is modest, a high velocity will result in substantial momentum. Is momentum a scalar quantity, something that has only magnitude, or a vector quantity, something that has both magnitude and direction? Pause here and check your answer. We just learned that momentum depends on both mass and velocity. So, since velocity is a vector quantity, momentum is also a vector and has the same direction as the velocity vector. Now, let us explore how we can manipulate the momentum of an object, say a tennis ball. To induce a considerable change in the tennis ball's momentum, what should you do? You give it your hardest hit and ensure a follow-through. In essence, you apply the maximum force over the longest period of time. This combination of force and time is what we call impulse. Impulse equals force times time. Impulse equals change in momentum. Ft equals delta mv. Are you ready to do more math magic? If we divide the above equation by t on both sides, we get F equals delta mv divided by t. F equals m times delta v over t, which can be written as F equals ma, which is Newton's second law. Therefore, Ft equals delta mv is essentially a different formulation of Newton's second law. Now, let us explore another intriguing scenario that might have piqued your curiosity. Have you ever pondered why a cup survives a gentle landing on a plush carpet, but an abrupt stop on an unforgiving, hard surface causes it to break. Join us as we don our scientist hats to unravel this mystery. Let us say that the cup has a mass of 0.6 kilogram and it descends onto the carpet. The change in velocity of the cup is 10 meters per second. The cup gently rolls about for 30 seconds and eventually comes to a halt. As the cup comes to a stop, its momentum undergoes a change of 6 kilograms meters per second, which is 0.6 kilogram multiplied by 10 meters per second. And it is the carpet's resilience that ultimately exerts the unbalanced force to halt the cup. The plush carpet, with its cushioning properties, allows the cup to gently come to a stop after it hits the carpet. Using the formula Ft equals delta mv, we can determine the force applied by the carpet to decelerate the cup. The impulse the carpet exerts on the cup amounts to a change in momentum of 6 Newton seconds. Consequently, the force acting on the cup is calculated as 6 Newton seconds divided by 30 seconds, resulting in 0.2 newtons. Now, let us envision the cup descending onto the hard floor at the same change in velocity of 10 meters per second and coming to an abrupt stop after it hits the floor. The cup's momentum undergoes a change of 6 kilograms meters per second, but this time it is the unyielding floor that delivers the unbalanced force to halt the cup. On the hard floor, the cup stops in a mere 0.5 seconds. Utilizing the same formula, Ft equals delta mv, we can compute the force applied by the hard floor to decelerate the cup. In this case, the impulse the hard floor exerts on the cup remains consistent at 6 Newton seconds. However, because it stops so rapidly, the force experienced on the cup amounts to 6 Newton seconds divided by 0.5 seconds, resulting in a much higher force of 12 newtons. Here are more challenge questions. In which case is the impulse exerted on the cup more? Pause here and check your answer. In both scenarios, the cup's momentum changes by the same amount, and the impulse exerted on the cup remains the same as well. If the impulse is the same in both cases, why did we get two totally different results? Pause here and check your answer. The key distinction lies in the manner in which the cup stops. On the carpet, the gentle deceleration is drawn out over an extended period, leading to a smaller force and a less painful outcome. Conversely, on the hard floor, the abrupt stop translates to a much shorter duration, causing a significantly higher force and an unpleasant outcome. Let us see what we learned so far. The faster and heavier an object is, the more momentum it possesses. Furthermore, momentum is a vector quantity because it takes into account both magnitude and direction, much like velocity. Impulse is the key to altering an object's momentum, and impulse equals force times time. If you change the momentum of an object slowly, a small force will act on it. If you change the momentum of an object quickly, a large force will act on it. Armed with this knowledge of momentum and the impulse-momentum relationship, we are better equipped to grasp the physics behind moving objects. Thank you.